Hello everyone. Welcome to the Programming and Data Structures Theory course in Autumn 2020 semester. Before we dive into the programming aspects, in particularly using C language to program something in a computer, we need to know or introduce that how such computing system in a generic way works, so that when you program something over these systems, how does it operate? So before we dive into the nitty-gritties of programming, as well as in particularly for your case C programming, we will see that how such a program get executed in a computer, and in general that how do we use a computer so that we could conveniently program and use the same. So to begin with, to give you a historical perspective, when the evolution of electronic computing has been for few decades from now. So when first the computing systems get evolved, then we see during the 1980s to 90s, your computation became free. So by computation becoming free, I want to mean is that your computer system becoming cheaper and cheaper, so that the number of millions and billions of computations that you perform comes at a very low cost if you compute the cost per computation. So it means that you have systems nowadays which are cheaper and it does billions and millions of computations in a second. So per computation cost becomes free. Then comes the era when we try to see the memory or the storage becoming free. So now easily you will find that you can purchase a very efficient and high storage pen drive having 128 GB with a very reasonable cost. Earlier, when we started in around 1985-90, the same cost would not give you any kind of a storage device at all. So therefore, when we evolve in this history from 1990 to 2005, we will find that the next decade of computing made the storage becoming almost free. Again, by free I mean that per capita storage becoming almost very cheap. Now you are in an era where you will find gradually after 2005, in this last 15 years, we are moving slightly towards communication becoming free. By communication becoming free, I mean that you see nowadays everyone has a cell phone and everyone has an internet connection. And it comes so cheap that you see that 1 hour of internet surfing is basically consisting of very cheap cost. So gradually, the evolvement of electronic computing started from evolvement of computing devices which made computation free. Then evolvement of memory devices which made the storage becoming free and portable. And gradually it moved towards the communication era which we are going through now, where almost the communication part is becoming free. So to know more details about the history, so here is a computer that was predicted, this will be a home computer in 2004, but now it was predicted in 1954 that this will be the size and the scope of computing in home. But we all have laptops, and we see that it has been a minuscule device has put in, and it has enormous power to compute. So this is what I mean by the computation is improving by leaps and bounds. So the storage, as I was saying, becoming free, because starting off with a magnetic tape drive, I don't know whether you all have seen this or not. So we move towards hard disk, and earlier it's a 5 MB hard disk. It's of this size so that it could be carried in an aeroplane like in this manner. And now easily you will get 128 GB pen drive. See, this is MB and this is GB. It's in 1956 and this is in current days. So you easily get such kind of a pen drive at a very cheap cost. So it made the storage per capita or per data storage becoming almost free. Finally, in the era of where we always do internet surfing, we Google everything, whatever we need. So you can see that from communication devices like this kind of phones, many of you may have seen this in your home, this kind of old phones where we have to rotate the dial many times to get the number going, to this phone which everyone has in their pocket. So see that this kind of a mobile cell phone has penetrated the general population so much that in the bottom figure you will see the usage of cellular subscriber base has been growing leaps and bounds, and it is up to 2007 first quarter. So, and usage of internet individually, I am not saying about the company, this is the individual usage of internet. So it makes, and it is possible only because the communication sector is coming to you as kind of a free device. So what all this points to the fact that the evolvement of such kind of electronic computing has made its own necessity to put in more and more sophisticated functional aspects. And when I mean sophisticated functional aspects into computing, it means that we need to do with the computer what we intend to do in a sophisticated way. And the only way we can talk with the computer in their language is by the help of programming. So that is a generic basis where more and more computing softwares, devices and electronic bases are improving, and therefore the necessity of such a course became eminent when we look around this kind of a history of computation. So the interfaces, that how we talk with the computer, as we are telling. So earlier, even I have not seen it. You forget about you have seen this or not. So it's kind of a punch cards to paper tapes, and then gradually we moved into keyboard based, where each key is the input from you towards the computer, and gradually we move towards this kind of virtual keyboard where a Bluetooth laser will create an impression of a keyboard and your hand will move over the keys so that the light that blocks, it will automatically sense that if you press the V, so the light that blocks coming here is up to V, and then through that it gives the input to the computer that which key has been pressed. So we have moved a lot from such kind of a punch cards towards a virtual laser keyboard right now in our disposal. So with this vast as well as fast environment of the computing spectrum, let us try to know how does the computing architecture or inside your PC, the devices, over which, on top of which we will try to learn program and try to talk to computer, but what consists of your inside devices. So if you open up any desktop PC, you will find the pieces which essentially give us this block diagram, which is the architecture of desktop PC. So you will find a processor. This is an old picture from 2001, that's why you see Pentium 4, but if you now find out, it will be either i3 processors from Intel, i7 processors, i5 processors. So this has been advanced processors nowadays. You have certain kind of interfaces as I am talking about. One is the USB interfaces, the position which you plug in your pen drives into. You will have CD DVD drives, that is one of the interface through which you can put things and talk to computer. You have the keyboards. You have another interface where you listen music, which is the audio output interfaces. So all these are interfaces have an internal controller, which is an input-output controller hub. There are memory slots. If you open up a PC, you will see this kind of slots, which is dual channel RDRAM slots, where you put in 128, this kind of a 4 GB, 128 GB RAMs. Those things you put inside these slots. So all this comprises of, and it is interconnected by this green lines, which we call as a bus, where the data moves through these devices, or the data from input output and the memory, and comes to the computing unit where it computes and performs the desired operations that you want to look. So this is inherently the block diagram. What you will see, if you are curious enough, you may just open up the CPU box and will see exactly these chips, these controllers are there. If you read out and try to search and find it, you will see this kind of architecture inside the computing system. So what this brings us to the fact that essentially a computer has a processing unit, which we call a CPU, has a memory from where we can retrieve as well as store the data, and has an input-output interface from where we can talk to the computer and can listen from the computer. For example, the audio devices. Now, having said this, essentially whatever we do on top of that, the body of the computer, that is the architecture, performs in these stages. Like if you want to compute something over the central processing unit, it will try to fetch the data or programs from the memory or from the input-output interface such as keyboard. It takes the program from the keyboard, or it takes the inputs from the keyboard, and it brings it into the functional unit which we call the arithmetics and logical operations in the central processing unit. So it first fetches, then it decodes in the central processing unit. It decodes that what do you want to do with those data, and it performs an operation which we call execution or execute cycle. So it fetches, it tries to understand by decoding, and it operates or executes and try to find out the solution. And then again it gives back the solution to the memory, and from the memory either it displays. So this way the processing unit processes. Now you may also refer that your CPU as a processor, and it contains multiple processors. Nowadays you will hear a term, there is multi-core processors. So by core you mean unit one CPU. So if you have quad-core processors, in your mobile nowadays it comes as a quad-core or octa-core mobiles. So this means you have 8 processors. So each processor can simultaneously do one task. So 8 processors can simultaneously tackle 8 tasks. So this is the computational power that we have nowadays in our devices. So it is quintessential that we know how to operate those devices through the machine language or the machine understandable languages, by which we will try to make our program and try to do whatever we intend to do. So basically, if you dig down to what a computing processing unit, this is your arithmetic logic unit which is responsible for your operations. There are many registers where when you try to take data in, the registers will contain temporarily the data, and it will give it to the arithmetic logic unit to process. Where in your program you are in, or where you are processing this program counter and other registers, you will gradually know in your course curriculum that all of these different registers will help ALU to process data and to get out the results. So inside a CPU, these are the overall blocks, the registers, the ALUs, and special kind of registers like PC, instruction registers and all are there. Then comes the main memory part, which tries to allow you direct access to the data. So it's all about, your device is all about how you store and retrieve the data and how you compute and perform operation of the data. The computation and performing the certain operation over data is the responsibility of the CPU. And the memory and its controller is responsible to give you back the data and take the data and store it in a proper place. And as you can see that nowadays the memory sizes, that is the size of the RAM, ranges from 256 megabytes from the old machines. Now you will see 8 GB RAMs in your laptops and desktops, 4 GB RAMs. So essentially when we are saying megabytes and gigabytes, usually 1K, it's 2 to the power of 10, that is almost more than 1,000. 1 mega means 2 to the power 20, it's 1 million approx, and 1 giga is 2 to the power 30, which is 1 billion approx. So that's why we call it as a megabyte, gigabyte and kilobyte, these 3 terminologies we will use. If you dig down to the memory, it essentially consists of an address and a data. So all the memory locations you see, it's a monolithic sequential numbering of the address followed by a data. So as if you can take an analogy from how your letter comes and placed into the letter box. So each unique location has a unique address where you can put in the data. So through the address, uniquely you can retrieve a data of any position and it will be unique. So this is how memory is being organized, or logically you can view the memory in this way as a combination of address and value. Finally comes the input, outputs and peripherals, that is your weapon to talk to the computer. So you see keyboard, mouse, this scanners and all these interfaces are one of the input devices. The output devices, you can see monitor as one of the output, the printer through which you print. and some of the storage peripherals which also you can store data and can send it to computer, that is your disks, maybe your hard disk, maybe your floppy disk, maybe your pen drive, the flash memory that we have. And in earlier we use magnetic tapes which has a sequential access, and obviously optical disk CD read-write CD drives you will see, where you put in your CD and can give the data from that storage. So this is the primary three pillars that you want to know is the primary architecture that are responsible for your computing. Your compute or processor unit, the memory from which the processor unit talks. This is not the peripheral memory, that is you store data and put into, that is the hard disk or maybe the external pen drives, external hard disk, all these. And there are input-output devices, keyboard and monitor you can obviously see from now. So with this background, let us first little bit go into that how a computer works. First of all, what is the primary difference between a calculator and a computer? See, one of the fundamental difference, as you can easily point out, that computing here in a computer becomes a general purpose. In a calculator, you have a stored thing. Only that you have a one particularly thing, that is the arithmetic operations you can do. Maybe in the scientific calculators you can do much more than only arithmetic, but the basic calculators that we talk about has a particular types of input that it can take and it could produce only arithmetic operations. However, the difference of computer being the stored program concept, that is that when you can in general, you can write your own and can dictate computer to do tasks in your own. So if you try to write some kind of program in the computer, it will do what it is being told to do. So there is no certain kind of only one thing in contrast to the calculator that we only do. That is, it is not the case that we only do arithmetic operations here. You see a movie in the computer. You open a browser and surf a net in the computer. Many things you write in a Word file in a computer. So all these different sets of activities can be triggered in a computer, whereas calculator becoming very special purpose. Since we started off with this program concept, then next question may arise in your mind that what it is that when you run a software, what is it? I mean, when you run a program in general. So basically it consists of set of instructions. That means it has a set of, so we write something line by line. Each line generates a set of instructions. That means you do this, followed by this, followed by this, followed by this. And a single processing unit takes one instructions at a time. Remember that fetch, understand or decode, execute, produce the result. Next instruction, fetch, understand or decode, execute, produce the result. In this way, computing device tries to see all the instructions and as a whole do a specific task. So now it is the onus of you to make the computer understand about the specific task. One instruction does not mean a specific task. For example, add instruction. If you want to, that will mean only addition. But suppose you want to add the number of students participating in each of the sports activities of the institute, then you need to write this addition operations on top of what is the overall activity you are trying to do. So that is your program. It consists of many things to do a specific task. Each of the things is an instruction to fire. So your duty is to understand the intent of the problem solving, the problem that you want to solve, write the program. The computer's duty is to fetch, decode, execute. And finally, when it does all the lines of the program that you have written, you will see your task is being performed and shown to you. Now, the third point is very interesting to look at, that we discuss usually in your general purpose machines. You will see there are two kinds of memory, maybe three. I will touch upon the third one very briefly. You will heard a term called hard disk. You will heard a term called RAM. Okay, random access memory. And thirdly, you also heard a term called cache. You will see L2 cache. You may be hearing the term L2 cache, L1 cache. So forget about the cache for the timing. For a general purpose, simplified machine, let us have a hard disk and the secondary memory of the hard disk and the primary memory of the RAM. So when you write a program and save it, so you create a file in your computer, write a program and save it, it is usually stored in the hard disk or the secondary memory. So it is kind of a dead thing which you stored or saved it. Now when you execute it by certain mechanisms that we will show and your lab classes will show you more, when you try to execute it, for example, you click on your browser to surf internet. So something gets executed. Then whatever for your browser, whatever program is written to run your browser, one by one fetch, decode, execute, this thing happens. So before that, your program, when it becomes active to participate or execute and show you something, your program will start to come in the primary memory or the random access memory during the execution. So please be careful in this understanding that your program, when you create and save it, it's a raw piece of program without being executing anything. It just stored in your secondary memory or hard disk. When it gets executed, it comes in the RAM, then goes instruction by instructions through some mechanisms, magic mechanism right now, goes to CPU and execute so that the task that you want to perform gets performed and you see what you intend to see. So this is how the overall concept of working of a computer, as well as on top of that how our program fits in, that we will learn in the overall course. This is all about the running and working principle of a computer with a program. Now the question is that since we need to also do arithmetic computation, so program inherently in a computer should also have to know certain number systems and all. So we are particularly accustomed with the decimal number systems. Basically decimal means that it will round up to 10. So from 0 to 9, and there is single digit, then the next digit of 9 will become, that 9 will be 0 and just before it will be 1 because so 9 we can consider it as 0, 9. So 9 plus 1 will be 10. So we cannot hold two digits in a single place. So it's 0 and 0 will be moved to 1. So this is the decimal thing we know, that which has power of 10. So this is, I think you all can understand, 234 is this. 2 into 10 square plus 3 into 10 to the power 1 plus 4 into 10 to the power 0. However, in binary system, which is mostly used in computer, we have two digits. So the first number is 0, 0, the second number is 0, 1, then the rotation comes, 1 cannot be 2, so 1 can come back to 0, and if it is 0, 1 is the number, then the first 0 will become 1. So the next number will be 1, 0, then 1, 1, then 1, 0, 0, and so on. So this is what we call as the binary system. So every digit has only two numbers to take, 0 and 1. And you can see in decimal, the leftmost into 10 to the power 2, so 10 square. So this is leftmost into 2 square. Middle into 2 to the power 1, the rightmost into 2 to the power 0. So this is your decimal. Similarly, the binary to decimal, if you convert it, you will get this way. So computers work with the binary numbers. The primary reason being that you see that if there is, so internally it has certain threshold thing to cross by some voltages and current in the internal electric circuitry. So if certain threshold is obtained by voltages, current, whatever it may be, some magic threshold is obtained, then over that threshold it is 1, below that threshold it is 0. So it is very easy to dictate between whether something is present or absent. So therefore, the access of the data is binary, or the working of the data in the computer is using binary numbers. So since we are trying to learn the language of a computer, not our mathematical language now, so we need to know what are the juggleries present in, or the jargons present in this so-called binary language. So bit is one digit of binary, single binary digit, 0 or 1. A nibble is 4 bits. A byte is a collection of 8 bits, and a word, it depends on a computer, either it's a 4 byte or 8 byte. So a pertinent point to note here is that you have heard about that it's a 64-bit machine. It's a 32-bit Windows operating system. It's a 64-bit operating system. We'll come to the notion of operating system a little later, but this means that at a time you can access these 64 bits. If you probe the memory at a location, at an address location, you can access this 64 bits at a time. So that is the size of the address bus, or that is the size of the data bus that you could push in your data through. So typically we call it one word access. So one word is 32 bits or 64 bits. In modern day computers, mostly we see 64-bit machines. So to give you a more what we call a formal view of decimal and binary number. So a k-bit decimal number is from 0 to 10 to the power k minus 1. If it is unsigned, only use a positive sign. So for k equal to 3, you can easily see with 3 digits, you can write up to 0 from 000 to 999. Similarly, for binary numbers, if you have 3 digits, you can write up to 000 up to 111. So 111 is 7, because 1 into 2 to the power 2 plus 1 into 2 square plus 1 into 2 to the power 1 into 2 to the power 1 plus 1 into 2 to the power 0. So it is 7. So we can express from 0 to 7 in 3 digits. So therefore 0 to 2 to the power k minus 1, here decimal becomes 10, here binary becomes 2. So for k equal to 8, with 8 digits, you can find that a number which is not signed, that is a positive 0 or positive integers, you can write 0 to 255 in decimal number with 8 binary digits. So with that, we come to a position where we understood that how a computing device tries to execute certain programs or so. But the only thing that is still magic what we see in this lecture is that even if I do not write programs, even if there is nothing, that how does the computer runs inherently within itself and tries to do something, that how do computer know that how it will execute the program? I have not written the program to execute it. I written a raw piece of file. How does it reads and tries to do whatever that file wants to do? Who writes those programs? So to know a little bit, what I would say in a broader way, we have two kinds of software. One is application software, one is system software. So whatever we will see here in this course is trying to write the programs in the form of an application software. So to do a particular problem, your browser is an application software. Your editor, Microsoft Word, whatever editor, Notepad, everything you use is a software. Your media player through which you listen to song is a software. It's an application software. Now, how does these application software run in your computer? So there must be some mechanisms inherently in your device that helps these to run. So the mechanism, the way you will run these programs that you write, somebody has to write that also, that how it will interact with your raw hardware, your CPU, your memory, how the data will come into the bus and give it to the CPU, how this fetch, decode and then execution, these things will happen from a raw piece of thing you are writing. So all these are part of system software which helps running other programs. That your C program will be run by somebody else and shown it to you. So only thing is that you are performing a particular task, but to talk with the computer there are many steps which is all a part of a system software. The operating system is one of the things that you all know. Maybe you are using a Windows, or some of you may be using a Linux. So it's a system software which tries to help you about running everything in your computer. Gradually we learn there is something called compiler, which takes your program, raw program that you wrote, raw C program, and tries to generate a machine interpretable language form which operating system can talk with the machine and can execute. So we will see very briefly that how this happens. So before that, we need to know what are the languages that computer understands. So first of all, everything is binary, and the intuition comes from the fact that inside it, it's an electronic and electrical devices are operating. So beyond a threshold is 1, below a threshold is 0. So we only know binary. So machine language, so whatever you see that I see an instruction, everything is binary. You will see only 101, 100, this kind of thing is coming in my data bus. Your 64-bit, 32-bit thing is only consisting of 1 and zeros and an instruction, which we demarcate as an instruction. So this is what we call as a machine language, which is directly understood by computer, and it is not portable because it's machine to machine, it varies. Program written in one type of machine using such machine language, if you at all can write, then it will only be specific to that machine. So it is very difficult because if you want to write, you need to remember that what does the corresponding binary number for add means. If you want to add two numbers, then you have to know that, let's say 10110011 means add. So you need to write that way. So it's very difficult. So therefore we do something one step above in the abstraction, that instead of just writing it in terms of a binary that 10110100 is add, we can use a mnemonic add to write the addition. So here it's nothing but, see what the burden of computers inherent, what we call system software has to do. When you write ADD, it need to convert it magically through system software, which you do not write, but system has to be in this language, so that machine, which is a machine language that computer understands. So one step transformation is a magic kind of from your perspective, because you will write something ADD 1 plus 2. Okay, ADD 1 2 will give you 3. So what does ADD means from a computer perspective has to be translated and simplified to a computer in machine language. So these are all system software. Even if you write it, this translator is not portable, because like machine language, so this ADD may be from our side we know, but from computer sides it's very specific, so it cannot be translated. So we call such kind of a translator is which translate from assembly language to machine language an assembler. So it takes a assembly language program and translate it. It's very difficult to use because you require many instructions to solve a program. For example, you see here, it just does a average between with 3 numbers. So what usually in C we write x plus y plus z. This is 3 numbers in 3 so-called variables. By 3 is my answer. So this one line, if you have to write in assembly, you have to write it in this way. What does it do? From right to left is usually the assignment happens. So first I move the value x to A. Then I add whatever is there in A with y and place the result in A. Then I add whatever be there in A. Currently in A there is x plus y. So I add it with z and place it in A. Then I divide A by 3. Whatever be there in A, I divide by 3 and again place it this. And then finally I move the answer to the result. So these so many assembly language instructions you need to give. Whereas if you write in one line, it's very efficient to write and it's portable, because this x plus y plus z by 3, you take it to another computer, it can also execute. One pertinent point again here is that provided you are writing in this language, computer only knows binary instructions to fetch, decode and execute. Therefore, from this language, a compiler will translate it to some kind of an executable code, and then your assembler will try to translate it into a machine language. So this compiler, assembler and the operating system finally tries to execute, fetch, decode, execute, perform this operation are the system software, and the thing that you write in this level, that is taking an average in a simplified form in your C language, is your application software. I hope it made you clear that it's you in a blink of an eye, when you click something from your desktop or from your laptop, it opens up. But see that it's an application program on behind it runs. In between that program, there are calls in the computer's own system software which takes that program and translate into machine language and then help operating system takes it and uses the architectural features to compute and give back the results. So this, though we are mostly concerned in this course about writing it in C or in the highest abstracted level form, but I want to give you this flavor because this is very important to know how these things overall operate, and maybe in future you may also be interested to write such kind of system software which is inherently a program. So it is none other than a program, and you will be amazed to know that your whole operating system of Unix and Linux is written in C. Your operating system, Unix or Linux, is written in C language. So your system software is another program, your application program is another program. Application program takes the help of a system software to run and execute and show the results. That's the bottom line till now. Now, gradually we are moving towards our code. So we started off with the computing devices and the history of it. Then we make sure that how our architecture looks, how in the body it happens, how it happens. Then we come down to a language kind of a framework which talks to it and which invokes certain operations to perform the activity. Now we are in our business. So the high level languages, which is not the machine level or assembly language, which we call low level, very difficult to code, maybe specific to a machine and that. Now we try to see how this C, C++, Java, Python, all these names you see are high level language, which is basically easier to use and give you a better kind of an abstracted view of what you want to do. And then it requires a process of translation, as I already told you, that is a compiler, assembler, the software, to make it into machine language and run it over your machine. So the benefits of using such kind of a high level language is the ease of using, and secondly, the portability across machine. You write a C program, you give it to your friend, he can run in his own computer, in his home, if he has the proper compiler as well as assembler and all these installed in his machine. Operating system, assembler, compiler, all this installed. So this gives us to a position where we will see that effectively what happens when we write a high level language program in C. So first you compile and make an object code. And you see in your program, gradually you will see that you will write something to take inputs from your keyboard. You will write something to show it on your screen, that is your monitor. So all these are the program that you do not have to write. You are only writing what you want to do. I want to average 3 numbers. Now see, averaging 3 numbers require to enter and take the values of 3 numbers from an user through keyboard. After average, you need to print the results in your monitor. So there are certain default activities or this kind of programs already written, which we call as libraries. You do not have to worry about that. You just say that print this. You just say take input from this. You just say take one integer as input in your program. But those are also programs and they are called, in the libraries they're already there. So they'll get linked into your object code wherever you invoke such kind of a, or you call such kind of an activity. And finally, you get an executable code, which is a raw piece of code where every line of is an instruction. And if you execute the whole thing, fetch, decode, execute, whole thing one by one, you will exactly see the result. As an example, you will exactly see the average value. So this is the whole framework. You write a C program, your program gets compiled, builds an object code. There are certain inherent libraries inside which you need, which gets linked into your object code and make the final executable code. So therefore, 2 steps we need. One is this compiling and linking. It's a one step which we call a compilation step, and finally the executable code to execute. So whenever you write a program in labs in your home, you will see whatever be the process you write and execute a program, you have to build or compile, which sometimes we call building, build or compile, and then you have to execute or run. These two steps will be there. So build and compile is just the compiler plus linker, all these activities. From executable code to run is using your system software to fetch, decode, execute and provide the results finally. Now comes the big boss, which we will say that the operating systems, which makes the computer convenient to use, because it is on the back of everything. Whatever you try to do, it helps you to do. So basically, it understands only the machine language. So you need on top of that those system software to make it into a machine language form so that it gets readable by the operating systems and performable. So you will see different categories of operating systems. Sometimes it is a single user operating system. Sometimes it's a multi-user. So multi-user sometimes shares in terms of time, that first 1 hour is this, second 1 hour is this. Hour is a very bad term here, but think it in this way. This is a time sharing machine. I share a certain time quantum. After that, you share another time window or quantum. There are machines which are multitasking. So it has a very big, rich theory that what is multitasking. I'm not going into the details in this course because beyond the scope of our thing. It's a they are a real-time machine. So you may use Windows 10. Some of you may use Unix, which has a free version called Linux. Now you will see Debian, Ubuntu, everything, Fedora. There are many kinds of Linux versions available. So these are the popular operating systems that we see. Now I just give you a question to think about, or maybe search and read about, that how multiple users can work on a same computer. So you see there are multi-users computers. Sometimes in a server you compute, multiple users are doing it. Multiple users are connecting to a server and running something. So how does multiple user can work on a same computer? Just think about it. It's nothing specific to this course, but just for your curiosity, you may think and read about it. Some of the terminologies that you need to know is, you have heard this flowchart and algorithm, which is basically a formal step-by-step procedure of solving a particular problem. So the role of computer programming or learning to program is, the broader role is nothing but to solve problems. So when we say that we solve problems, that means there should be a step-by-step procedure to solve it. And that is what algorithms or flowchart gives us. Then finally, program becomes a translation of that overall flowchart into line by line writing of a particular piece of code or C program, for example, line by line encoding whatever you have written in your algorithm into that form so that it could be processed by the computer. Compilation, remember, compilation, linked, execution, system software are there on your back to do it. But from thought process to algorithm, that is step-by-step flow, and from step-by-step flow to writing proper programs is what you are going to do in your course. Typically, we write using C, C++, Java, Python, this high-level language. In your course, you will use C. So this is a summary of what is a program and the software. So since you already had a flavor of it, so programming is a process of writing instructions in a language that computers understand. Just like your mother tongue. So when whoever speaks in your mother tongue, you can easily understand. So computer essentially understands machine language only in binary. But to our benefit, there are system softwares which helps us in this process. So we can write it in a more readable form of a language, though not in mother tongue, but in such kind of a language that computers can understand. C will be one that we will use it here. So program and software, I am not going into the details because this you have much elaborated it. It's a sequence of instructions or tasks, and programs for doing tasks on computers is called as software. So now coming down, since we gradually moved into our course topic, that is how to write programs and how to conceptually think about solving problems using programs. So we start with how to writing programs. So very broadly, 3 steps, as I mentioned: write a program, save it. If you remember, it gets saved into your hard disk, secondary memory. Compilation, The program comes into your primary memory, compiled, linked. Running the program means the execution. Then fetch, decode, execute. Over all the instructions happens. Finally, you get the result. So 3 steps. You write your program. You compile. Sometimes this compilation is also called building step. You run. That is, you execute the program. Or use the computer to execute it. To give you an example of your first C program. So, first of all, a very brief example. So, whatever we write using /*, it's the comment line. So, I just have a comment here. So, these are libraries, as I was telling. So, this program just prints in the first line. If you write this program, compile and execute, you will see it will print welcome to IIT KGP. \n means it will give a new line. \t means it will give a tab position. That is a particular space you will see in the beginning. Maybe 4 characters, 8 characters, however it is set in your computer. It can vary. And then you are doing PDS theory, full stop. These 2 lines you will see when you run the program. As I am saying, see, as I was telling that you are not writing this printf things. Printf is another library functions or maybe another program that you are using. You are telling to show me this line, welcome to IIT KGP, just by calling this printf and writing it in one line. So this is another program which is there in the library which we call as stdio.h, which we include. So in this library, so whenever your compile and linking gets on, so you will link it. So sometimes in mathematical operators, if you want to do x to the power y, you include math.h and you link certain libraries to do that. So this is a structure of a very basic structure of a program. So main is something you have to have once in your program, and operating system tries to find main and start executing line by line the instructions. So for the timing, just remember that this get translated through your compiler. This gets translated to executable code. Then it gets into a machine language that it understands, and operating system tries to find where is your main and tries to execute one by one the instructions. So what this particularly means, what this all are in this whole course, we will try to see one by one. Now, you will see the structure of a program. If you see, it will consist of functions that we call this main is also a function. Printf we are calling is a function. We will gradually see later. Then one function is main, as I have said. It will start the program from there. There will be assignments, arithmetic operations, conditional. You will do many times same task again and again, which we call looping. All these are in the part of the course syllabus, which we will cover in the due time in this course. But the statements are executed in a sequential, that is one by one manner from top to bottom. So first this one will be executed, second this one, and third this one. Just to give you a brief insight about if you made a mistake, let's say in this main I put the opening bracket but do not put the closing bracket. Then what will happen is that you will obviously get an error, since this is not the language that your computer fully understands. Suppose to a foreigner, I just talk in my mother tongue, one of the native language in India, he will not understand because all the characters are not matching its own. The sentences are not forming that way. So therefore, if you just eliminate some of the intermediate pieces from here, sometimes you will get a bug. And there is a very famous line that to bug is human and to debug divine. So you are doing a divine activity if you debug it yourself. Okay, on a lighter note. So then what you do, you again save the file, compile it, you will see there is an error. And many compiler gives a different types of narration to the error. So it's a syntax error because you have this opening but not the closing brackets. Sometimes nowadays the editors are so smart that they automatically show you that you have not closed your bracket. That is one of the benefit. But there are small errors that happen that often doesn't caught your editor. Because let's say if you do not put the closing bracket here and also miss the opening bracket in printf, then what will happen? Your editor cannot give it because this opening bracket has a closing match here. you miss the closing bracket as shown here, and for the time being think of missing the printf after printf the opening bracket. So those kind of errors are also caught using compilation phase. When you try to make the instructions, you will find certain kind of problems again. So I request you, when you first write a program, you try to do some nuisance to it. I mean, you try to remove something, you try to write some garbage into it and see how the errors are coming, because that is also be a good lesson to you, because you yourself has to now debug since you are writing it. So you go back and correct the error and save file. Then finally you will see, as I already told, welcome to IIT KGP in the first line, and the next line with some space being in the left you will find, and then you are doing PDS theory, ending with a full stop is printed. So now accessing from users, you have to, so printf is showing whatever you computed to the user. Now if I want to take something from the user, there is another, in your library, there is another thing called scanf. So you scan, here I scan an integer number. All these details, just keep your curiosity going on. These details will be elaborated, why there is an and here, what does this means and all, in the next few weeks of lecture. So I just scan here a number and try to print that number here again. So therefore I say enter how many students. It will wait here after the first line unless you enter and press the enter key. So you write 180 and press the enter key, immediately this line will come. So scanf will keep you waiting inside the program, and the program will wait for you to enter something. So as I already told, that there is a language that computer can understand. It understands letters from capital A to Z, capital lowercase a to z, digits 0 to 9, and certain special characters. Here is a set in any standard book or even in internet you can find it. So C program does not contain anything else. It contains these things, and every character is from this set. And there are certain things called keywords. In the next week it will be more clear to you. So if you look at this program also, I have used something called int, which is already known to your computer. So these are called keywords. Return, I have used return. This is another keyword. So these keywords you cannot use as a name of the variable. So this we call as a variable num. So int means it's an integer number. So num, you cannot write int and you give the variable name also something like return. You cannot write int return, because return is also a keyword. So you need to avoid those. There are many of them. We will gradually learn this. So with that, let us try to finish off these lectures where we started that computer program is omnipresent everywhere. Anything you can think of, you will see computer program is there. Even if you are listening this video on YouTube and you see that there are small pieces of programs people have written. One is the showing of the video, how to accessing, how he's showing, how your progress bar is showing it is almost ending and you are impatient to when it will end. Think about very minute details of programs that also there in the back end. When your network is not so strong, you will see some blurred video is going on rather than a high resolution video is coming to you. Some program is running for that too. So even if you do not imagine something, there is a program behind it. Airline reservation system, how you call an Uber or you call an Ola taxi, and how does it find a route to the destination? How does you get the traffic where the road is congested? How does the Mars mission, in the Mars mission, how does the rocket deploys at a particular position? So everything, you're playing from a chess to speech recognition, everything is a huge piece of program coding is going on. And to give you an idea, you see the lines of code that make it. So Windows 7 has almost 40 million lines of codes. Your HD DVD player has 4.5 millions. Space Shuttle has 0.4 millions. And your Facebook has 61 millions. Can you imagine that the Facebook that you use on behind it has 61 millions? I have not put the code, the number of lines of code in Google. It is 2 billion lines of code is there in. But most interesting fact I will come here to know that nowadays you will find many autonomous car, and even in the high-end cars, you will see there is an automatic control, some mechanisms that some switches do something. So there are enormous codes put into your high-end cars. There are many softwares run in your cars nowadays. So typically high-end Mercedes-Benz car nowadays has 100 million lines of code. Remember, Facebook has 60 million. Okay, the Boeing, the aeroplane that you use, Boeing 787 has kind of 13 to 14 millions. The Android mobile device you use, in the back end, it has 11, 12 millions of code. But your car nowadays have 100 millions or so. So things are changing. Programming is becoming more and more important in every domain, in every sector, be it agriculture, be it mechanical, be it civil. So there are abstractions to solve problems and to think about how to solve problems and see it by doing a program to simulate what you want to do. So with that note, I just finish up this lecture that since your computing landscape has changed, so this is a very pertinent time to learn programming and to see the enormous scope of programming and to apply it in Facebook, in agriculture, in high-end cars. Anywhere you see that we can have enormous scope of this kind of an activity. So welcome to programming. I end up with a geeky joke, I would say, but even if you are not, some of you may not understand, but it will get understand. You just keep it in your mind, you will understand after a due course. So the teacher asked the student, how would you write a C program to prevent Titanic from sinking? Student writes in one line, float Titanic. Float Titanic. Why the student told will be revealed in the next few classes. Thank you for your attention.